Good morning, everybody. My name is Peter Corless. I am here today with David Kjerrumgaard. Uh, we are going to be talking about data streaming quality of service for Kafka. So what is that and how are we going to do that? Let's get into it. First, I want to introduce David further. He is published author of Pulsar in Action. I've known David for years. I used to be at ScyllaDB, and that's where we first ran into each other. I was working at a big NoSQL vendor, but he has stayed consistent with Apache Pulsar, definitely knows his stuff in streaming. I actually came into this sideways. I've worked for, again, ScyllaDB and now StarTree, where I'm working on real-time OLAP. So I'm not actually in the streaming space, but we are a receiver of real-time streaming. And so we have opinions on how real-time streaming should work. Now let's get into what we came up with. Last year at Real-Time Analytics Summit in 2024, David and I were talking about why we might need quality of service for Apache Kafka. And the main reason is because Kafka isn't just Kafka anymore. If you take a look at the world of Kafka, there is still Apache Kafka, but there is Apache Pulsar, which can read and write from Kafka topics. Confluent, of course, has their own core engine. Red Panda is available. WarpStream takes Kafka and puts it on an S3 storage system. There's also Kafka without Kafka, like Estuary Flow or Amazon Kinesis, which is a Kafka-like protocol. And so what you can see here is that there's a mix of things that are similar to Kafka or need to integrate with Kafka that are for streaming services. And we can't guarantee that everything is just Kafka, nor can we guarantee that all Kafka clusters are going to be deployed the same way. Some might be running on local NVMe, very fast local storage. Others might be running on S3. We know that Apache Kafka doesn't require at-rest encryption, but some people really might want to have encryption. So we know that there's these fundamental differences, inequalities, and we know this through our experience or through documentation that there's differences in what Kafka is, how it is deployed, how it's managed, etc. And we know, for instance, that different Kafka cluster sizes might provide different latencies, different throughput guarantees, and different data retention. So what we're looking to do, especially as we're moving into a future world where we're going to have agentic systems doing more automated management, we want to be able to formally declare these differences so it's not just in an SRE's head, but the systems can intercommunicate these standards of what kind of a Kafka are you and what kind of service guarantees can I get. So again, right now, it's up to an SRE or somebody who's provisioning the data pipeline to go, okay, well, I have this producer producing 100,000 objects per second. Here's a consumer group that might be able to consume that, or may, again, because you have consumer group scalability, you might be able to scale up to that 100K per second. But maybe another consumer group may not be hardware provisioned to be able to meet that rate. So there are standards right now for how quotas can be applied for byte rate thresholds and for CPU utilizations, but this is generally per broker. It's not really a cluster throttling, and it's not really per customer. You can do producer throttling or rate limiting yourself, but it's not really part of the protocol as it is right now. So again, you can still have one consumer group totally fine with consuming from the fire hose, and another one might say, please downsample this so that it's at a rate that I can look at it. But there's no automatic way of doing that. And then the other thing too is that that's dependent upon a producer behaving a certain way predictably. But we know that sometimes there's stochastic variations when you might have a certain rate and then all of a sudden, let's say there's a huge error log rate jump. And so suddenly there's a lot more errors coming through. So suddenly the pipeline is going to be jammed packed. The producer is going to have this stochastic variability, and maybe the consumer groups were fine before, but now they certainly can't adapt to this new world, even with auto scaling of the consumer groups. So, and the other thing too is that it might not just be a stochastic change in the rate of data throughput. It could also be a change in payload sizes. So maybe everything else was 1K, 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 packet sizes, and then all of a sudden you get an object that's a megabyte or 100 megabytes. What do you do then? So we want to be able to describe the fact that these topics could be highly variable. Producers can have, a huge change in patterns, or maybe you want to say from the producer side, I am not going to do this to you. I will not pull surprises. But we need to be able to declare those things and then be able to monitor them and watch to make sure that they aren't behaving irregularly. So how will we do that? Well, here's one of the ways that you could create an adaptive system with quality of service. The first way of, let's say you have these two consumer groups, one is able to scale up to 100K objects per second, another one was limited to 50. One way would be to kind of push upstream the fact that you did have a limited consumer group of 50K objects per second and ask the producer to downsample. And so it would kind of fork off a different process and do its own downsampling for the second consumer group. Or if the cluster was a sophisticated piece of intelligence, the broker cluster might fire off, let's say, a Flink job to do the downsampling and then send that topic to the second consumer group. And these are two ways that could be handled if you had this kind of end-to-end quality of service idea. There could also be different faster and slower lanes. So maybe you do have one version of your Kafka is running on NVMe, local NVMe, so it's very fast I/O, very high throughput. Maybe something else is running on Amazon S3, and that could be a slow lane. And so for users that want to say that they want to get end-to-end latency guarantees of less than 10 milliseconds, you can run on one fast lane, and then maybe another producer group might say, well, I'm okay with just having stuff get there within 10 seconds, and they could go to a different consumer group. So that's just an example of how quality of service would shape, like, where would you direct your traffic? Right now, you would have to run completely separate clusters, but in theory, you could have an intelligent cluster with some local NVMe and with some S3, and the cluster would be able to navigate and say, well, this is the latency guarantee you want to have. Let me store it a different way. Let me shape it a different way. And of course, there can also be more complex things of, let's say, tiered storage. So data within the last 24 hours would go on fast NVMe. Data beyond 24 hours, we can move to S3. We can architect for that if there was a standard way to be able to understand these kind of negotiations for quality of service. The other thing too is that this is the dawning of the age of elasticity. A lot of Kafka services are kind of provisioned and they're set. And of course, with anything that requires a significant amount of rebalancing, it's very difficult to just take a stateful system like a Kafka and say, well, now give me another petabyte of storage. That's not the way Kafka works today. But in the future, we can imagine that with Kubernetes and with more advanced methods of provisioning, you could see in the future these more elastic kinds of systems. And of course, the commercial vendors are there already. StreamNative, Confluent, they do have elasticity and dynamic provisioning. Apache Kafka vanilla? No, that's something that you'd have to do yourself a little bit. So again, I think we're going to see more of this as we go on. And again, like I said, it's not going to be magic. There is a scale up time, even when you have dynamic provisioning. So what you may want to have in this quality of service is a way to say, okay, well, I'm going to need this extra capacity at noon on Saturday, when the big game is showing. So, scale up around that time and then maybe scale down 3 hours later. You can have more predictive sorts of windows of this stuff of, scaling up and scaling down, but you need to still make a provisioning request. Hey, this is how I need you to shape your cluster. We don't even have a grammar for that yet. Everything right now is manually done by an SRE team. You're filing tickets, and that's not going to that's not going to work for the next decade. We know that's not even working now. It takes a lot of manual work to do these kinds of scale up, scale downs. There's a lot of please mother may I. There's a lot of rigmarole to get these kinds of things. And none of this integrates with, let's say, advanced billing or accounting systems so that as you're provisioning up, it you're getting foreknowledge of the fact that this is going to change your bill in a certain way. So this does not mean that every Kafka cluster will have to have elastic scaling. In fact, many of them will not. But without this kind of standard, there's no way we can manage dynamic elastic scaling except through that kind of ticketing system where a human needs to be involved. So now I'm going to turn it over to David, who will talk to you about how this is going to happen using open messaging.
Thanks, Peter. When we first spoke, we were focused on the Apache Kafka project for this concept. However, we've since broadened our perspective to recognize the universal benefits across all messaging systems. This isn't just an Apache Kafka problem, it's also a RabbitMQ problem, it's an ActiveMQ problem, it's a JMS problem. This is why we came up with the concept of a new platform agnostic protocol called StreamQoS, which is short for Stream Quality of Service. This protocol will enable dynamic performance configuration between messaging clients and the corresponding systems they wish to communicate with. The purpose of this protocol is to establish a standard method for all messaging clients and infrastructure providers to negotiate service level agreements concerning key messaging system attributes, such as performance, like latency, cost, how much you're willing to pay for the service or topic to operate, and resilience, how many copies of the data do you need, how many AZs does it need to be deployed across, etc. This way, clients can communicate the requirements to the messaging platform ahead of time and thereby allow these messaging systems to respond accordingly, either by scaling up the infrastructure, or if the messaging system is incapable of meeting these clients' requirements, they can inform the client ahead of time before it connects and has degraded performance capabilities. As you can see from some of the key features listed here, this new quality service protocol gives messaging system clients finer grained control over individual topic characteristics. By negotiating specific service level agreements, users gain more control over performance, costs, and the underlying storage mechanisms. For example, they can specify, I want to use object-based storage, or I want to use NVMe drives. And this will be communicated ahead of time to the messaging system. This protocol's design also allows for future expansion to accommodate ever evolving needs as messaging systems evolve and requirements become much more specific around different protocols. For example, the protocol could be enhanced to track the messaging system's adherence to the pre-established SLAs and trigger remedial action to the cluster. For example, if I, as a messaging system, agreed to provide message latency of under 50 milliseconds, and I'm tracking that performance and seeing that I'm routinely violating that, I might have to proactively start scaling up resources or maybe switching to a different object storage requirement and letting the client know ahead of time that this is what's being involved. So a lot of different capabilities here, and we're only scratching the surface. The StreamQoS protocol is currently in draft status, and we are actively soliciting feedback from messaging and streaming experts, as well as users of messaging system as well. All are welcome: cloud vendors, streaming platform providers, anyone who consumes data. The purpose of this discussion is to encourage contributions to the protocol and help refine its specification, right? This is a collaborative effort that will facilitate the integration of the StreamQoS into messaging systems like Kafka by the KIP 1182 that we already discussed, or Apache Pulsar, or RabbitMQ, etc., thereby accelerating its implementation and turning it from more of a concept into reality for consumers and users of messaging systems. Now we've decided to move. The goal of the StreamQoS is standardization, right? Therefore, we've opted to develop these concepts within a technology neutral framework rather than focusing on a KIP or a PIP or some other message, each messaging platform trying to replicate that. We wanted to take a step back and move it into a more standardized format, into a global overall governing body, such as the Open Messaging Framework, which is renowned for its standardized benchmark tests and supporting diverse messaging technologies, right? This is the ideal platform. It's founded under the Linux Foundation, so it's open to all. And we've decided to propose not only to introduce this messaging protocol here within this framework. By standardizing these quality of service concepts within these diverse messaging systems, enables users familiar with other platforms to readily understand and utilize them, right? This promotes a common framework for discussing messaging system topics that we can all discuss, whether we're using NATS or Pulsar or KIP or JMS or some messaging system that hasn't been developed yet. We'll all start with an understanding of what we want to talk about from a client perspective in terms of latency, throughput, et cetera, and have the underlying messaging system implement these automatically. So we have one concept as we have concepts of topics, and consumers and producers will have the concepts of QoS baked in an open messaging framework that's governed under the Linux Foundation. From an operational perspective, implementation of this protocol would allow for a single endpoint that can host topics with vastly different quality service requirements. Currently, different clusters with different URLs and credentials to connect to them would have to be used to provide this capability. The quality service guarantees would be dynamically negotiated between, the client and the server based on the client's needs and the server's capabilities. If the server is unable to meet the requirements, one possible solution would be to provision new infrastructure to accommodate the workload, making the cluster adaptable to the workload over time. The server is responsible for tracking these capabilities and its performance, and may scale or reconfigure dynamically resources automatically. So as new producers come on, they could demand more throughput, it'll scale up. As consumers start going away and less consumers, less producers to the topic, it may scale down to save costs. All this is baked into the protocol, and it's dynamic. At the end of the day, the server needs to know what is expected of it from the clients in order to meet those expectations and adapt accordingly. So as you can see here, the StreamQoS protocol aims to manage the quality of service at the topic level. From a conceptual level, QoS requirements are based on a per topic basis. It doesn't make sense to have it at a cluster basis and have multiple clusters. Instead, you want to address these various requirements such as latency, throughput, and costs at the topic level. So again, you'll define things in terms of percentiles. I need my P50 latency to be no less than this, my P95, et cetera. Same for throughput, same for availability, et cetera, et cetera. What protocols I want it to support, what storage format do I prefer, what optional features do I need as well, right? So additional concerns such as multi-protocol support and back storage implementations are all covered on a per topic basis. On the server side, it's based on a protocol where it will accept these offers. The client will connect and say, this is what I require. And it accepts these requests, and it will respond in turn with, this is what my offer is. And we'll talk about this in a minute. This is what I'm capable of providing, either based on heuristics, based on what I know. If I'm an NVMe drive based, system, for example, I can provide these very low latencies, but it's going to be high cost, et cetera. So these things are built in. Or as it tracks this information and how it's performing, it could give you real metrics based on what it's actually seen and what's measured, right? So my throughput, if you want to connect to an existing topic, I know my throughput on this topic is here. These are the numbers, take them or leave them. That sort of thing can be baked into this as well. So our initial protocol draft is based on a protobuf definition. This is a low-level messaging protocol that a lot of messaging systems use at the client server level to communicate, allowing clients to send these requests to the supporting servers. And again, upon receiving this request, it can either respond with success, failure, or pending status in case it's doing some scaling to the infrastructure. It'll say, okay, I can't handle that right now, but if you give me a few minutes, I'll let you know when the cluster's up and ready and I can meet your SLA requirements. So again, it's designed to be a negotiation process, and this is it at a high level, very, 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 very high level. We'll walk through some examples here to give you more feel for how it works. But at the very, very top level, the client starts the process. It tries to connect. It's saying, hey, I want to produce to a topic, and and it sends a quality of service request to the server, which then responds with what I mentioned before is a quality of service offer, right? So it'll say, hey, this is what I want. I want P99 latency of this. I want throughput support of that. I need message level encryption, for example, and I want object-based storage. And the server will respond, with an offer saying, this is what I have. I can provide up to this level of guarantee. And then the client really has three different options at that point. Now it can interrogate the offer and say, oh, this meets everything I want. This is great. And it can accept it. And at that point, it has to, send basically, I'm accepting this pending offer, letting the server know this is great. You don't need to renegotiate with me. And then I spin and poll periodically, make sure that topic's available. Maybe, for example, it's a newly created topic. I got to wait a few minutes for that topic to become available. Or I can accept it and say, give me a callback URL. Say, hey, that's great. I accept this offer. And then please notify me at this callback URL here, this webhook, to let me know that the status is up and running. And now I can trigger, my client can proceed and start producing messages. Or, it can also reject it and say, no, outright, I don't need this. This is, way too expensive. The cost per gigabyte is too high. Or, I don't want to use object-based storage for whatever reason. Or it can go back and forth. It can do a negotiation process. It can do a counter offer, things like that. Asking the server to scale its infrastructure, things like that, to modify its behavior and sort of negotiate back and forth. Well, I'll decrease my latency, or I'll increase my tolerance for throughput, or whatever it might be. So it's a back and forth process. So let's look at a few concrete examples to bring this more from the conceptual into reality, and how you can see it again at a conceptual level, from a coding level, protocol back and forth here. So again, you can see things. First scenario is just going to be the client intends to connect to a topic called payments.secure with very, very stringent low latency needs. As you can see by the P9, the P50 and P99 latencies, all, double digits, very low double digits, but also very low throughput. I'm not sending a lot of data, but I need to send it very quickly. I need it to be resilient, so I have a very high uptime. This is a mission critical payment process use case, for example. I'm willing to pay a premium for this sort of performance. I'm willing to pay a certain amount per megabyte, but I need multiple protocols. It has to be encrypted, processed exactly once. I prefer attached storage versus object storage, so I'm willing to use local disks. I understand implicitly that I'm going to need that for my performance. And I can tolerate up to 2 AZ failures. So this is going to require the topic to be deployed across at least 3 different AZs to tolerate 2 of those failing and continue to work. And then again, to specifying bytes as a standard format. Maybe you want to use JSON, Avro, protobuf. Anything here is available for right now. Just bytes would be the example. So in this scenario, the client sends over this request, and then the server responds accordingly with this offer, right? It gives you a cluster ID so you can look up information. It's a currently active topic, says, hey, I already got this one. These are the latency numbers I'm seeing. As you can see, they're all pretty good. They're all, at or below the latency numbers required. Throughput numbers are great. Uptime, everything, looks good. Everything's supported. Since this topic's already there and the server gives back the latest performance stats, again, this is sourced directly from the metadata it has. The client should evaluate this response, and because it offer meets all the criteria they asked for, the client should just accept it and connect, right? So this is a very simple, seamless process of going through connecting to something it wants for low latency and high durability. In this scenario, the client would want to connect to an IoT sensors topics, and it wants to use MQTT protocol. It doesn't care what else is supported. It has to at least support MQTT. And it also, has, higher latency. It could tolerate some higher latency, but also has higher throughput requirements, et cetera. It also prefers object storage as a storage type. As you can see, the server's QoS offer response indicates that the throughput and SLA requirements are not fully met, right? So there's some miscommunication here. I need, 5 megabytes per second. I can only do 1.2. So up to this point, now the client, can do a lot of different things. It can either accept this offer, just say, okay, I'll take it. I wanted this. This is what I wanted, but I'll accept this as is. It could propose a counter offer, send another offer back, indicating that it does not want this. The server would track this additional information and say, oh, this is additional request, and maybe it would, do some auto scaling at this point, or scale up the cluster to increase the throughput. And if this counter offer is made, the server might then choose to do that, by potentially adding another broker to the cluster, or the client could just refuse it and say, no, this is not acceptable for me, throw an exception in the code, or trigger some other response. to maybe try a secondary cluster that exists outside of a QoS supported cluster, for example, and handle all those things. So, hopefully this gives you a good idea for how this would work in general, a little more concrete implementation ideas. Peter's going to talk a little bit about a more complex scenario where there's some negotiation going back on and forth, but hopefully this adds to this. And with that, I'll hand it back to you, Pete. Thanks so much.
All right, thank you, David. I think this is just an example of how much we can do with technology right now, with where we're taking this protocol right now. And what we'd like to see is this applied to Apache Kafka through KIP 1182, the Quality of Service Framework. So the first thing, like I was saying before, is that you need to be able to make these quality of service declarations. I am a producer. I will be producing X. I am a cluster. I can handle this amount of throughput. I can probably guarantee these kinds of latencies, and I can provide this amount of persistent storage. And then for consumers, hey, I'm an elastic consumer group, but I can only scale up to this, and then of course you can also say things like, and by the way, I don't need anything more than 24 hours old, or I need a month's worth of data backlog, right? So producers, the cluster, and the consumers each need to have their own declarations of who they are and what they can do and what they want. Then there needs to be cluster capability descriptions. So am I doing storage tiering? Am I capable of auto scaling? Am I capable of doing self-balancing? And what kind of limits are there around this? If I can do provisioning of additional storage, is that limited to a certain scale, or can I scale to infinite? Maybe, maybe not. So again, clusters themselves need to be able to say what their capabilities are. Do I do encryption at rest? That's a good thing to know. And right now, when you publish to a topic, you don't know whether it's actually encrypted or not when it gets to that cluster. So I think these are the kinds of things for the cluster capabilities. Next thing is this QoS negotiation. A producer might say, hey, I'm producing 100,000 objects per second, whether you want it or not. The client's consumer groups right now could push back and say, well, I need that downsampling like we talked about before. But this needs to be a negotiation between producers, the cluster, and the downstream consumers. And right now, there's no grammar for this. This would provide a kind of a grammar to make these kinds of requests. And again, maybe there's a way of doing things like downsampling or data retention or anything else like that. This would allow for that kind of negotiation. And on top of all this, this is what you say you want. You say that you want 10 milliseconds end-to-end data latency. Did you get it? This requires instrumentality across this entire data pipeline, real-time data pipeline, to say from the producer to the consumer, this was the end-to-end latency, and to be able to measure that request to the actual performance. So observability integration is going to be key to make sure that you're meeting SLAs that you've auto-negotiated here. And then there's also, in the topic configuration, we may be able to create templates or governance guidelines that go along with the topic configuration itself. So all of these are part of the concept of the framework. And in fact, each one of these can be blown down into very specific specifications for how are we going to do that exactly. And so just as an example, here's some of the metrics, the measurements and the responses we want to get. So latency, here's what the latency I want to get to, and here's the latency I actually saw. Here's the throughput I wanted to have. I wanted to get this number of objects per second, but I only was able to get that. Or I'm going to tell you, I'm giving you a fixed rate of throughput. I'm not going to vary for this, or be ready because my mode will be around this many objects per second, but you might see a burst up to this kind of max, right? So to be able to do throughput guarantees or throughput requests is going to be important for the standard. Payload sizes, is everything going to be less than a K, or are we going to see large objects coming down the pike? And if so, some people are going to bark at that and say, well, that's fine. You can send me a 100 megabyte object, but I'm going to discard anything greater than 1 meg, right? So we need to have this kind of understanding in the whole overall pipeline about what happens when things are supposed to happen and what happens when you find those anomalies. Availability, I want to get this level of message delivery success. Maybe some people can guarantee that, maybe others can't. Durability, so I want this triple replicated, or it's totally fine. I'm fine with a single copy of this in the cluster, but that's going to be important for some people. The data retention period, we've already talked about this, and with tiered storage, you might need to have a more complex grammar here, where retain this in fast NVMe for 24 hours, then ship it to S3, and after maybe a week in S3, it can blow up. So time to live and things like that is going to be very important for a retention period kind of grammar. And then cost sensitivity. All of this is great, but tell me, what is the chargeback going to be? And this depends upon whether it's an internal system, whether this is a service provider that you're getting like Kafka as a service. All of this requires a lot of forethought here, and it's not going to be done like anytime soon universally. Like we'll each every single provider is going to have to take a look at what is their grammar, how are they going to negotiate these things with their customers. Internally, how do you account for these kinds of things? There's a lot of work to be done. And when we put this forward, we understood that this is going to take a long while for the industry to make sure that all of their systems are tooled and instrumented to be able to do this. And then there has to be a way for individual organizations to be able to cater this towards their own specific internal needs. So there'll have to be extensibility to the grammars that we're providing here. Also, metadata is going to have to go with these different topics. So what's the topic name for this policy? How do you identify a policy uniquely? So it could be a UUID or it could be a ULID. There's other ways of tagging this to make sure that this policy is, this is the unique policy, or maybe there needs to be a hierarchy between policies. So an overarching hierarchical policy and then down into individual departments or topics, etc. We need to have versioning on these policies. We know how schema versioning alone is a great thing to have to manage these days. So there's going to have to be policies on this quality of service as well. And then how do we want to store this? I think, this is the easiest one to solve for. We just put an ISO 8601 format, and hopefully, that gives us a way to do timestamping on these things so that we can say this policy will be active starting at this time. So you can make these kind of proactive requests for, please put this policy in place by this time so that we don't miss Super Bowl traffic. And then here's the next thing is what's the negotiation process going to be? And there's a lot more work here to do in terms of like diagrams of back and forth, so how do you open up a request? How do you make your requirements clear? How do you get counter offers or denials? How do you do the exact sort of relationship diagram between two different entities or more entities, from the producer, the cluster, to the consumer, and all the way back to the producer, to make sure you have this kind of end-to-end policy agreements in place? So there's a lot of work to do. Me and David have started this process, but this is where you're going to be able to get involved, because every single Kafka protocol compliant system will have to do its own tooling, its own instrumentation. Don't anticipate, David or I to pick up the implementation for your particular technology. Every single vendor who's doing a Kafka compliant system, every client, consumer, every producer needs to think about this from their context. I know I've been talking internally with people here at StarTree, and it would be interesting for a database to be able to say, here's how much we can ingest on this StarTree Apache Pinot cluster. And then how do we push that back up the chain to the producers, right? So how do you do backoffs? How do you do, again, all sorts of things that are interesting from a database's point of view. So we're taking a look at this internally as well. And this is where we're looking for other vendors of software. Maybe you're doing something with Flink. Flink is going to have both a consumer side of things as well as producer side of things. And so it's going to have to think about, well, what can I do? What is the latency for processing on a particular Flink job? Not every Flink job is going to be of the same weight. So, perhaps you need to consider, like, what is the internal mechanism by which we can determine things like latencies and latency guarantees from consuming to producing data out of a Flink job? Interesting question, right? So here's how to get involved. The first thing to do is check out the KIP itself. It is published on the Apache org side for Kafka. And there's also a discussion thread. If you join the developer thread for Apache Kafka, there's a wonderful thread there. And we will have other ways to get involved. And if you'd like to reach out to myself or reach out to David on LinkedIn or on any other social platform where we reside, and introduce yourself and why you'd be interested in this protocol. And for that, I just want to say there's going to be a lot of questions I anticipate, so please get in touch with us. And on behalf of David and myself, I just want to thank you and thank the audience and thank the Kafka community who has built such an incredible technology. And now we're just going to take it to whole new levels. Thank you very much. Have a great day.
Awesome. That was phenomenal, David and Peter. Thank you so much for that content. I thoroughly enjoyed the session. So I think for the attendees, if there are any questions, please post them in the Q&A section. I know somebody had raised a hand momentarily, and I don't see that person right now. But I think, yeah. So I think, while we wait for questions to come up, anything you want to add to what you already covered, Peter or David? Something. Yeah.
Yeah, I wanted to point out that it's a thankless job to file a KIP because you have to sign up for the Kafka Dev mailing list. And so even though you wanted to file one KIP, you get to see news on every single pull request and every other KIP. So you basically have to take 1,000 arrows in return for just firing off one. So that's probably one of the greatest learnings I have. David, what was the biggest learning for you going through this process?
Well, yeah, you kind of took that one from me, but it's my biggest learning is my concept of how people would address this quality service is completely different from others. And so by talking to other people, I get another perspective on how they want to talk about data, right? Our goal was to invert the way people think about topics and think of it more as a client and how I want to consume data and having that refinement. And everybody has their different little nuances or things that matter to them versus others. So I have my thoughts on performance. Other people's have on data quality and data assurance. Other ones have on cost, and they're all equally valid. And so building this framework out that people can start thinking about it in a different way is a first step. And I think it's an interesting space we're getting into now, right? Now, I have to think about, I have one statically defined cluster that has certain capabilities. Now I have elasticity. Now I have multi-protocols. Now with our Ursa product, we have swappable engines and storage formats. So you can have one cluster do everything for you. You can sort of be a central location, which is a logical way to think about it. So that's what I learned as well.
Yeah, I think that what you're saying is very true. Once this comes out in a usable form, everybody's going to want to use it in a different way. And it reminds me of the old children's story of the little red hen, right? Everybody wanted to eat the bread that the little red hen was going to bake, but nobody wanted to help grind the grain, right? Nobody wanted to help knead the dough. And it's like everybody wants this to be done, but the number of people who are actually going to be committing code to this right now is just like yourself. I mean, I have to admit to people, I'm the guy who came up with the idea, but if I'm doing code, something's gone desperately wrong, right? So this is a call to the community for us to get other contributors, especially David's going to probably do this for Pulsar. He's going to focus on where he needs to focus for his day job. And so core Apache Kafka people need to kind of step up into this. And I think that's going to be an interesting thing, is that this is kind of like a rap battle. You're throwing down, and you want to hear some people spitting bars back at you.
Yep. Great point.
Absolutely.
The other thing that I found out, I think we were talking about this backstage, but one of the things I found out during the research for this was that Kafka doesn't guarantee encryption at rest. And I was like, what? Like it just came to my mind, like, wait a second. I mean, because so many Kafka type systems like Pulsar, you guys do encryption at rest, right?
Yep, absolutely.
But Kafka itself has no guarantee for that. And I
Mhm.
could imagine that one of the key criteria for a lot of people doing quality of service is like, please make sure my data is encrypted in transit and at rest.
Yes, I would agree. Absolutely. So yeah, there's just so many things. This is a great, like you said, it's a manifesto. It's a way to rethink the way we deal with messaging systems. I think it's a great start in the open messaging framework, and I think good things are ahead. I'm looking forward to implementing some of these things, and then people looking at it say, "Wow, this is great. Why did we do this all along?" So that's
Exactly. And I'm hoping that this is going to have like there's implicit in this is the fact that there's going to be years of work ahead of us,
oh
right?
yeah,
This is not like a one and done kind of thing. There's probably going to be a lot of child KIPs that are going to file off against this, and PIPs, as you said, and even MQTT can get into the action.
yep, yep. And then MCP servers will do it all for us.
In theory, no, but I think that's a good point, is the fact that MCP, like you guys were just showing today, MCP can now do potentially like interrogation of your topics and then, start to alter them. And when you have an agentic AI system that can adapt the system to the way the users need it to behave, you can see on the producer side, the broker side, and the client side these end-to-end architectures where they're all negotiating with each other for these different contracts for specific topics, and again, not all consumers and producers are created equal. So I think it's going to be key for us to be able to have this grammar so that they can negotiate this on a machine-to-machine level, as opposed to an SRE talking with the data engineering saying, "Well, I can't do that for you today, and but come back to me next Tuesday,"
Right,
right?
right. Yep, for sure. Absolutely.
All right.
Cool.
So those
I
are
think
some of my thoughts. Kundan, what were you thinking?
No, no, absolutely. I think I completely agree with some of the things. I think I was thinking a little bit about that encryption address as to, won't you run into some of the, compliance issues, like, larger enterprise asking like, is that even, there would be a checklist thing that what? I mean, this might be a difficult one to go through. I don't know if they, like, most of the Kafka vendors add anything proprietary around to kind of support it, but I think, that's definitely strange not to see that in Kafka. Um, I don't see any other questions right now. Looks like I think there is a closing keynote, right? I think or something. So perhaps people might be kind of exploring that one as well. So any closing thoughts if you want to add before we go, or last 10 seconds for anyone to post questions for David and Peter?
Get involved.
Yeah.
We want your feedback. That's the whole point of this. It's a discussion. It's the start. It's not the end. So get involved.
Exactly. All right. Thank you so very much,
So
David.
much.
Thank
Thank you. Have a
you
great
so
day.
much, Peter and
Thank you,
David.
everyone.
Yep. Thanks
Goodbye.
to all everyone for joining. All right. Take care.